Hello guys, we're going to have a little look at quantitative chemistry together. How I'm going to do that is basically by looking through your notes, which you should have at home. So it would help if you had them out in front of you as you look through this video. We're going to look at some examples as well and work through them. You may not need this whole video or this whole topic. You might just need to skip back and forward within the video to find the wee bit you're getting stuck on and have a look at that. So we're going to start, the first bit of your booklet is talking about the mole. I'm going to come back to that in a separate section. We're going to start with this idea of relative masses because that's actually quite an important concept in quantitative chemistry. When you're talking about mass to elements, the mass you probably are thinking of is the mass number in the periodic table. So if you look up carbon in your periodic table, you'll find these two numbers beside it, a 12 at the top and a 6 down the bottom. Hopefully you remember from the first topic that the 12 at the top is referred to as the mass number. So carbon's got a mass number of 12. And you should know that means that is the number of protons plus neutrons in the nucleus. Now in some ways that doesn't make too much sense as a mass because we don't really know what the mass of the proton and neutron are in the nucleus. We just know that there's 12 of them. What we're actually doing when we're talking about the mass of atoms is just kind of comparing them to each other. If I put magnesium beside this carbon, if you look it up, it's got a mass number of 24, atomic number of 12. Now, again, we still don't know what these actually weigh, but we do know that because magnesium's got a mass number 24 and carbon's got a mass number 12, magnesium must be twice as heavy as carbon just because it's got twice as many protons plus neutrons added together. So that comes together when we're defining the relative atomic mass. This word relative means comparing to. So we're comparing atomic masses to each other. You've got this slightly complicated looking definition which can unfortunately come up in the test. The relative atomic mass of an atom is the mass of the atom compared to that of the carbon-12 isotope, which is a mass of exactly 12. There's a couple of key points in that definition. First thing is just as I said, we've got this comparison. So we're comparing different elements to each other. You might be a wee bit confused by why we've got carbon mentioned in the definition. It was just a handy reference element that they used when they're working out all the different masses, so it's kind of in there for historical reasons. They just picked carbon-12 to be like the standard when you're working out these masses. The definition is one thing, but in actual fact, you don't really have to do too much complicated work out the relative atomic mass. You're basically looking up the mass number in the periodic table. So there's a few ones here. Sodium, if you look up its mass number is 23, so its relative atomic mass is just 23. Bromine has got a mass number of 80, relative atomic mass is therefore 80. Fluorine is 19, fluorine again is still 19, hasn't changed. And sulfur is 32 and magnesium is 24. So long story short, if they ask you for the relative atomic mass of an element, just look for the mass number in the periodic table. Now, little kind of tangent here, little side bit. You have come across this idea of relative atomic mass before in the first topic about atomic structure. You can still be asked, as you did in that topic, to calculate that relative atomic mass, which involves, if you recognise this kind of average calculation where you add up all the masses of the isotopes divided by 100. Not going to go through that here, but just in case you want to work through those, I'm going to give you the answers just so you can reference them. With lithium, the relative atomic mass would be 7.6 times the mass number 6, plus 92.4 times 7 over 100. That would give you 6.92 to 3 significant figures. Bromine, you'd have 50.7 times 79, plus 49.3 times 81 divided by 100. That gives you 80.0 rounded to 3 significant figures. Copper, 69.2 times 63, plus 30.8 times by 65 divided by 100. Gives you 63.6. So that is true in the first topic. It is still true now. You can calculate these masses as well given average isotopes information. So working out the mass of an atom is one thing. You can also be asked to work out the mass of a formula, and it's got a slightly different name. Instead of relative atomic mass, it's now called relative formula mass. It's not too much different though. Essentially, if they give you a formula, or you have to work out the formula sometimes, all you do is work out what atoms are in that formula and add up the mass of all those atoms. So really a simple example would be water, H2O. It's got 2 H's and an oxygen. The mass of a hydrogen is 1, so 2 ones, 1 plus 1. Mass of an oxygen is 16. 1 plus 1 plus 16 gives you 18. And you got a couple more examples there. So you might have done this section already in class. If not, pause the video here, have a wee go and see if you can calculate all these masses. Just be careful again with ones with brackets. You have to make sure you add up all the masses within the brackets. So the number on the outside multiplies everything inside by that number. So I'm going to very quickly give you the answers here to that. CO is 12 plus 16 is 28. MgO is 24 plus 16, which gives you 40. H2O2 is 1 plus 1 plus 16 plus 16, which gives you 34. Sulfur dioxide, SO2, is 32 plus 16 plus 16, which is 64. Na2O is 23 plus 23 plus 16 is 62. Al2O3 is 2 27s and 3 16s, which gives you 102. AlOH3 is 27 for the aluminium. O plus H, 16 plus 1 is 17, so 3 17s for that bit gives you 78. MgNO3 twice, 24 for magnesium, 14 for the nitrogen, 3 16 for the oxygen, but that bit has to be times by 2. Add that together gives you 148. CSO4, 64 plus 32 plus 16 times 4 gives you 160. K2SO4, can't remember the mass potassium is, but ends up being 135. And this one, aluminium, 27 twice plus 32 plus 16 times 4 3 times gives you 362. With the challenge questions at the bottom, if you attempted them, it's not too much more difficult. You just have to swap and drop it first. Potassium oxide is going to be K and O. Potassium in group 1, so K plus. Oxygen is in group 6, so 2 minus, just by using your group rules. Swap and drop the numbers gives you K2O. Adding up that mass gives you a mass of 94. With sodium nitride, sodium is in group 1, Na plus. Nitrogen is in group 5, gives it N3 minus. Swap and drop those numbers gives you Na3N. Adding that up gives you 83. Cesium sulfide, cesium is very big, but it's just in group 1. CS1 plus, S2 minus, because sulfur is in group 6. Swap and drop them gives you CS2S. Adding that together gives you 298. And the final one, iron 2 fluoride, the II there shows you iron with a 2 plus charge. So Fe2 plus, fluoride's in group 7, so swap and drop that. FeF2, which gives you a mass of 94. But long story short, essentially, if you can see the formula, if you can use your mass numbers in your periodic table, you are just adding those numbers up. The last little bit in this section on working out relative masses is this kind of side calculation about working out the percentage of an element within a compound. Now, you have got a slightly scary looking formula which you can use if you like formulas, so I think in a lot of cases you might not need this. It's easy if you just look at an example. Now, there's one about sodium hydroxide here. It's written out in lots of words. I'm just going to do it at the side here. If you think about the formula NaOH, something you could do very quickly is just work out its relative formula mass. We've done that in the last section. Sodium is 23, oxygen 16, hydrogen is 8, is 1. So that gives you a mass of 40. The question might therefore be, calculate the percentage of the mass that comes from the oxygen. Now, a wrong way of doing this would be to think, okay, there's 3 atoms there, therefore it's 1/3 each, or 33%. But that does not include the fact that these all actually weigh different amounts. We talked about the fact sodium weighs 23, oxygen weighs 16, and hydrogen weighs 1. So they're not all contributing the same amount to that mass. If I wanted to work out the percentage that comes from the oxygen, I would have the mass that comes from the oxygen, which is 16, and then divided by the total, which is 40, and then times it by 100. So the fraction just becomes very simple. 16 over 40 times by 100. In the calculator, that gives me 40% of the mass is coming from the oxygen. The only thing that would make that a little bit more complicated than this first example, if I have more than one oxygen in this formula, I would have to multiply it up. So if it was, I know it's the wrong formula, but if it was NaO2H, I'd have to have 2 times 16 on top there because there's twice as many oxygens in that particular formula. So if you look at the couple of questions down at the bottom there, again, have a go at them first if you haven't got them done already, but I'll work through them here. Percentage of copper and copper sulfate, so I look at my formula, CuSO4. First thing I would do is just to work out the mass of the whole thing. Copper 64, sulfur is 32, 4 16s for the oxygen gives me a total mass of 160. The mass that comes from the copper is just that 64. There's only one copper there, so that's all I can do. So the fraction therefore becomes 64, the mass from the copper, divide by the mass of the whole thing, what it's out of, 160, times by 100, which gives you a mass, or a percentage mass of 40%. The second one's a little bit more complicated because there's a bit more going on. The percentage of oxygen in aluminium sulfate, Al2SO4 3 times. Again, first thing I can do is just work out the total mass. So 2 aluminiums, 2 27s. Inside here, that's 32 plus 4 16s, but all together that's 3 times. That should, if I've calculated this correctly, give you 362. Have to be really careful with the oxygens here because there's not just one and there's not just 4 of them. It's SO4 in here, which gives you 4 oxygens, but there's a 3 around the bracket of this SO4. If you think about how brackets work, everything inside the brackets has to be multiplied by what's outside the brackets. So 4 times 3 gives me 12 oxygens in that formula. So therefore my fraction becomes 12 times 16 over that total, which is 362, times by 100, gives you 53%. The final type of example to look at is this one, which is a little kind of harder example I can maybe bring up. In this case, you're not being asked for the percentage of an element in the compound, but you're being asked for the percentage of like a part of the compound. One example would be this one here. This magnesium sulfate, but it's got some waters attached to it. It's got 7 H2Os in the formula. Looks a bit complicated, but just treat it like that. It's MgSO4 with 7 H2Os attached to it. The question might be, what percentage of that mass comes from the waters, the H2O part? So in terms of the theory, it's not any different. It's just the numbers become a little bit more complicated to work out. Again, start at the same point I've been starting at before. I'll try and work out the mass of the whole thing. So that's written down here. So 24 plus for magnesium, 32 for sulfur, 4 16s, 7 18s is what a water weighs, gives you 2, 4, 6. So I've worked out that the mass of the whole thing is 246. The mass that comes from the waters must be just how many waters there are times by the mass of one water. The mass of water is 18, 1 plus 1 plus 16. There's 7 of them. Therefore, 7 times 18 gives me 126 in mass of the water. So the fraction becomes 126 divided by 246 times by 100. That's 51.2% H2O. So I'll have a quick go at these two down the bottom now. The first one's it's very similar to this. This one's a wee bit different, but I'll have a look through them now. Copper sulfate. It's got 5 H2Os beside it, so there's 5 waters attached to it. Have to work out the percentage of the water. Again, start by working out the mass of the whole thing, including the waters. So that's 64, 32, 4 16s, 5 18s for 5 waters. That ends up being 250. The mass that's from the waters is just 5 18s. So that becomes 5 times 18 on the top, divided by the whole mass, 250, times by 100, gives me 36%. So this one's a little bit more complicated. The percentage by mass of the sulfate ion in sodium sulfate. First things first, I need to work out what sodium sulfate is. If I look at my periodic table, sodium is in group 1, so it's going to have an Na plus charge. Sulfate's on the back, remember, SO4 2 minus. If I swap and drop that, it gets me Na2SO4. So I need, of the total mass of the whole compound, what mass comes from the sulfate? That's what the question's asking. I start by normal, work out the mass of the whole thing. So 2 23s for the sodium, a 32 and 4 16s gives me 142 for the mass of the whole thing. The sulfate ion is just this bit. So I need to work out what mass that has and then divide it by that 142. So that's 32 plus 16 times 4. That goes in the top. And I need to divide it by 142 for the total mass. Times by 100, make a percentage, gives me 68%.